Welcome to the TerraTherm webinar series. The topic of today's webinar is when is hotter better? And I'd just like to, in addition to welcoming everyone, provide you with a little sort of introduction by way of this is the second webinar in a series that TerraTherm has offered. If you're interested in listening to a past webinar, you can go to our website to Library Webinar. And this particular webinar will be also available at that site by tomorrow. Please make use of the chat facility in GoToMeeting to ask your questions, although we will go through them at the end of the half hour or so presentation. And then we'll be available for up to a half an hour of Q&A after that. Also, when you choose to log out, there'll be a survey. We'd very much appreciate it if you'd fill it out. So I will begin now. This is when is hotter better? Effective treatment of higher boiling contaminants including chlorobenzenes, PCBs, and dioxins. And I'm Ralph Baker, Chairman and Chief Scientist of TerraTherm. TerraTherm is a leading provider of in situ thermal remediation services. We were founded in 2000. In fact, I'm one of the co-founders of the company, and we've completed over 40 field projects on 4 continents to date. I have about 40 years experience in on-site and in situ treatment of waste in soil and groundwater. Many of you know me, but there's also some people that I'm not familiar with on the list of attendees, and I particularly welcome you as well. Thermal conduction heating is a process that is the focus of today's webinar. So let me explain it for those of you who aren't familiar. We install steel pipes in the ground. They can be vertical, horizontal, at an angle. And in each of these pipes, we install an electrical heating element, which you can see in red inside the figure to the left. This heating element operates when it's fully turned on at around 700 Celsius or 1400 degrees Fahrenheit. And it's much like the heating element on an electric stovetop in that we can turn it up or down. It delivers at the same wattage over its entire length, about a kilowatt per each meter length of heater. So it delivers heat very uniformly over its entire length. And that, coupled with the fact that the thermal conductivity of soils is a relatively invariant physical property, varies only by a factor of about 3 across a wide range of soil types, means that we can deliver heat to the surrounding soil very uniformly, even in the face of heterogeneous conditions. Of course, we have to be mindful of the groundwater hydraulics that are present. I'll get to that later. So heat moves out radially from each of these pipes, which, by the way, are about 3.5 to 4 inches in diameter, so they're very easily installed in a wide range of conditions. And the upper right shows the cross-section between 2 heaters. We have a bit of a Rorschach image there. You can see in it whatever you want, but the main thing that I'm trying to get across is that the zones close to heaters get hottest first, and then the material in between gradually comes up to temperature from the ambient temperature to the boiling point of water, and at which point we start to boil off water. If we boil off all the water, then we can get to higher temperatures, and 335, as you'll see, is a typical target temperature for a high boiling SVOC. So the heat spreads primarily by conduction. It's a very uniform process. The contaminants we can treat using TCH, pretty much any organic contaminant. Many of you are familiar with the bulk of the practice that we are engaged in, which is to treat chlorinated VOCs, and that's not the topic of today's presentation. People often ask, well, what else can you treat? And These include chlorobenzenes, PAHs, of course other VOCs, and higher boiling constituents, commonly referred to outside the U.S. as POPs, which include PCBs, the chlorinated pesticides, and dioxins, and also mercury, which of course isn't an organic contaminant, but can also be treated with this process. So there's two main ways to apply PCH, in situ or ex situ. And the ex situ form of it is called in-pile thermal desorption, or IPTD. We're going to focus first on in situ thermal desorption, or ISTD. And before I do that, this is basically just a glossary slide for those of you who aren't familiar with the alphabet soup that we use to describe various in situ thermal remediation technologies, including those that TerraTherm offers and a couple of others. I would like to note that TerraTherm made a decision years ago to focus on electric heaters as opposed to gas heaters. And if you're interested in the reasons why, please visit our blog. So looking at a spectrum of heating approaches from lower, moderate to higher temperature applications, it's the heating above 100 C that we're focusing on today for the treatment of SVOCs. And this is an effort to give you a sense of the applicability of thermal for SVOCs. I've broken this into two categories of SVOCs, lower boiling and higher boiling SVOCs. So at the top, the lower boiling SVOCs include compounds such as monochlorobenzene, dichlorobenzenes, and naphthalene. Naphthalene is a bit of a oddball because it shows up on both VOC and SVOC lists. We found that it behaves pretty much as a lower boiling SVOC, however. And then I've further broken it according to whether we're above or below the water table, and whether we're shooting for modest goals, such as 90% removal, or that might be commonly used when the goal is expressed as removal to the extent practicable of NAPL, or stringent goals such as greater than 99% removal. So 90% versus greater than 99% is quite different. And we see that much as we do with the widespread practice of in situ thermal remediation for treating chlorinated VOCs, that if the goals are modest, we can do it either above or below the water table with a range of technologies. But if the goals are stringent, thermal conduction heating, either in situ or ex situ, is pretty much the best way to go, the only way to go. And below the water table, we can only do that in situ if we dewater that zone. In other words, lower the water table below the bottom of the treatment zone and keep it there throughout the heating process. Now, down below, you see the higher boiling SVOCs, such as trichlorobenzene, PCBs, dioxin, pesticides, and mercury, which is not an organic compound, but it has a boiling point similar to that of the pesticides and dioxin PCB. And we can treat that with thermal conduction heating above the water table, or conceivably below the water table if the site is dewatered effectively. So here's a graph showing the vapor pressure of these various compounds as a function of temperature. On the left are the VOCs, TCE, PCE, and BTEX would follow right in that same neighborhood. Over on the right are the higher boiling constituents, such as PCBs, dioxin, pentachlorophenol, and benzoate pyrene would be up there, as well as mercury. And in between is this this interesting category, such as naphthalene and the chlorobenzenes, or chlorophenol, compounds like that. I would be remiss in not mentioning that we have treated coal tar sites at the boiling point of water and at higher temperatures, and we can effectively turn a coal tar that was liquid by treatment at the boiling point of water into what is essentially what's depicted in the center here, like a piece of asphalt, by driving off the BTEX and the naphthalene. That's not really the focus of today's talk, so that's all I'll say about that for now. Most of what we're talking about today is treatment on the right-hand side. So in a nutshell, and forgive me for those of you who to whom this is familiar, but there will be some new material in this talk, so stay tuned. But ISTD in a nutshell involves either vertical or horizontal heaters placed in a pattern. Generally, we heat the soil in a batch in the source area for 3 to 6 months. During that heat-up period, the soil contaminants vaporize and desorb from the soil. The vapors and steam that are generated once we get to the boiling point of water are vacuumed up. And then when we get to higher temperatures than the boiling point of water, we find that the higher boiling constituents, the POPs, will decompose in the soil. At those sites where we've had an opportunity to monitor that closely, we've seen 95 to 99% in situ destruction. But any remaining POPs will be treated in the vapor extraction system. So all this without excavation. And here's an example of an early project that was done with a horizontal thermal blanket by GE and Shell at South Glens Falls, New York. I think it's a good visual way to understand the effectiveness of removing organic material from the soil at these kinds of temperatures, because the surrounding soil is exactly what was underneath this area that has been cleaned, and the removal of the organics is quite pronounced. We've treated projects in every EPA region, with a preponderance of our work being in the Northeast and on the West Coast. Altogether, including projects outside the U.S., we've treated over 40 sites to date. And more, we see very large projects that we're working on between 50 and 100,000 cubic yards or more. So I will provide some examples of projects where these technologies have been used for treatment of higher boiling contaminants. And first, for PCBs, we stand on the shoulders of those who came before, particularly Shell TerraTherm carried out these 5 PCB projects in the 1990s. And a lot of what we know about treating the higher boiling constituents is an extension of what they developed. So at these sites, you can see very high pretreatment concentrations, milligrams per kilogram of PCBs, and basically non-detect concentrations post-treatment. These were very well-documented projects, and many of these papers are available on our website. Also, it's notable that the off-gas treatment concentrations were well below the standards. For dioxins, we have treated a number of sites, and I'll provide as a case study one in California. Very high pretreatment concentrations and concentrations post-treatment. These are mean soil concentrations in picograms of TEQ per gram or parts per trillion that are well below what is considered a very stringent cleanup standard for residential use. And the source testing that was done for the exhaust gas was well below the 0.2 nanograms TEQ per cubic meter that's a typical standard. And here's some data that you won't have seen us present before for chlorobenzenes, these intermediate boiling constituents. I have presented here both some work that was done trying to treat these constituents at the boiling point of water, 100 C, and above the boiling point of water. So we see a marked difference for the total chlorobenzenes, and this includes mono, dye, and trichlorobenzenes. Before treatment, high concentrations. Post-treatment, for the sites that were treated the way that we typically treat CVOCs, in other words, at the boiling point of water and maybe boiling off 20 or 30% of the pool water, we get about 90% removal, which is pretty good. But we can do much better if we go to temperatures above the boiling point of water. By the way, down here at this particular site, we boiled off most of the pool water, so it was a kind of an intermediate case, and it did quite well. But if we wanted to get to very stringent goals, we were able to do that by boiling off all the water. So as a full-scale example of ISTD for these higher boiling constituents, this is a project that we did for Southern California Edison in Alhambra, where we designed, constructed, and operated the system. And here's some of the construction drawings. You can see the drilling to install the wells, which were at this site as deep as over 100 feet in some places, average of about 20 feet. And here's the manifolds before they were jacketed and insulated, and to the right, how everything looked when it was ready to be turned on. The air quality control system took the vapors from the well field through manifold into a thermal oxidizer and serial vessels of granular activated carbon. And in addition, we had continuous emissions monitoring, and 4 source tests were undertaken and carried out by an independent stack testing firm. The emissions were clean and met the standards throughout. In terms of the heat up, here are curves showing typical representative thermocouple readings within the well field in between heaters, in other words, in the midpoint between heaters, for each of the 2 phases. And what we see in common with the 2 is that we get up to the boiling point of water and sit there. There's a plateau phase for both phase 1 and phase 2 until the water is boiled off, and then we're able to much more quickly increase the temperature up to the target temperature, which in this case was 335 C. A lesson learned has to do with what you see here for phase 2, where we had to actually ramp back the heaters because it turned out there was more contaminant mass at this creosote site in the ground than had been anticipated during design. So the thermal oxidizer wasn't able to keep up with all that. We had to back off and stay within the capacity of that air quality control system, and that just simply lengthened the heating period somewhat. Eventually we got up to the target temperatures in both phases, and this I think is notable because it represents the cooling that occurred. We used a wet quench to accelerate the cooling at that site. And here are the post-treatment, pre- and post-treatment soil concentrations on a log scale, showing more than 2 orders of magnitude, almost 3 orders of magnitude reduction for benzoate pyrene equivalents, and nearly as much for the dioxins, so that we met the residential cleanup standards for these constituents, that they were the contaminants of concern, resulting in a no further action letter from the California Department of Toxic Substances Control, releasing the site for unrestricted land use. And this was done at a cost about 40% less than the excavation cost would have been. So in summary, we met the goals in a very stringent jurisdiction, South Coast Air Quality Management District, and achieved no further action. And that's a very notable accomplishment in a site that was grossly contaminated with creosote prior to treatment. I mentioned briefly before that we've also treated manufactured gas plant sites. This is a gas holder that we treated in Massachusetts. and we were able to go to essentially similar treatment standards as what I just described in this particular project, but also removed all the coal tar from the bottom of the gas holder using a boiling point of water approach. And here's another site that I also presented data for earlier, a former drum site where there was chlorobenzenes and naphthalene. A more recent site in North Haven, Connecticut, where a pilot was carried out in this area up above, and we have a wide range of chemicals at this site, from CVOCs to SVOCs. So we had a wet quench and scrubber for acid gases as well as a thermal oxidizer, and as a result of this pilot, we've been selected to proceed at full scale at the site. Now I'd like to switch gears a bit and talk about the companion technology, IPTD, which, as I said before, is basically ISTD in a different geometry, where, for example, contamination is too widespread at a site and too shallow to afford efficient in situ treatment. It can be gathered up and treated on site in a pile, or a pile structure or a container. And this can be also used to treat any organic contaminant, but we think it basically makes the most sense for the high boilers. It eliminates all the issues related to off-site disposal, such as lots of truck traffic and neighborhood effects. And we found through examining this that it's highly sustainable to treat on-site if possible. There's usually a lot less energy used and much smaller carbon footprint to achieve residential type standards at this kind of a site. So here's an approach that it resembles in situ treatment to a large extent, but it's done in a fully insulated box with bottom, side, and top insulating covers, so that greatly reduces heat losses and optimizes the energy efficiency of this process. By contrast, here's an approach that we have patented that affords the treatment of much smaller or medium-scale sites by making use of a container that can be readily filled and emptied and loaded and unloaded with no obstructions. But the example that I'm going to provide of IPTD is a large system being done for the U.S. Agency for International Development at Da Nang Airport in Vietnam to treat dioxins. At this and some other sites in Vietnam, the U.S. military during the Vietnam War employed Agent Orange herbicide, and the constituents of the Agent Orange, 2,4-D and 2,4,5-T, remain in hotspots at this airport site. And as you can see in the northern part of the airport, this is shown here, this area it covers about 40 acres, and there's high concentrations of dioxin present at this site near neighboring residences. So altogether, about 40 acres were found to be contaminated, and a total of about 77,000 cubic meters, or that's about 95,000 cubic yards, that required treatment. An environmental assessment was done, and it was determined based on that ISTD, IPTD could meet the goals with certainty, be implementable, and be comparable in cost to the other available techniques that were looked at, which basically landfilling. And a treatability study showed that once we got to 335C, If we stayed there for 21 days, we could reduce the concentrations by 3 or 4 orders of magnitude down to the concentrations desired, which at this site are 150 parts per trillion. So as a result of that, in February of this year, USAID awarded us a $37 million contract to implement IPTD there. And it's being done in 2 phases. The first phase largely soil and the second sediment. The pile structure is complete and the well field and treatment plant are now under construction. The heating of phase 1 will begin next year. So there's the airport and the pile structure, just to kind of orient you. And this little video will give you a better idea of what we're doing. Da Nang is the #3 city in Vietnam, in central Vietnam on the coast. You'll see the airport and the northern part of the airport, and we'll begin to descend to a level where you can see the pile structure and how it was built. First, the pad was prepared, and then precast concrete blocks were installed to create a pile structure. And inside that pile structure, a floor was poured to create a bottom, and then insulating concrete, a gravel layer, and a leachate collection system. And then trucks were used to bring the contaminated soil from around the site and fill the various lifts at appropriate density and moisture content. Once that was completed, then a gravel layer was placed over the surface of the contaminated soil to serve as a plenum for vapor extraction. And then we installed the 1,250 vertical heaters into this area, and we did that in only 18 days. So it's a very efficient process. And then once, and you'll see these heaters installed in just a moment. First the gravel layer, and then the heaters falling from the sky. Once that was done, we then poured a lightweight concrete cover to serve as insulation. This is the manifold vapor extraction system that went in before we poured the cover. And also a system for being able to add air to the pile. So if we zoom in on the corner, you can see the concrete blocks, the bottom, the gravel layer at the bottom, and the insulation, both in the bottom and the sidewalls, steel sheeting, the leachate collection system, as well as now the soil is placed in, and you can see the ability of the leachate to be removed. The vapor collection system in the gravel plenum at the top underneath the concrete cover, and then the heaters delivering heat, as I described for ISTD, and allowing the collection of the vapors into the overlying vapor collection system. The vapors travel to a treatment system, which we're in the process of installing right now. You can see the electric substations. By the way, the power is being provided from hydroelectric plants that are in the area. So it's green power at this site. And the vapors and steam come to this treatment system, where a system involving 2 technologies is being used: macroporous polymer extraction and adsorption on granular activated carbon for treatment of the vapors and liquids, so that a clean discharge will result. This is in the process of being built right now, and as I mentioned, we'll be turning it on next year. So stay tuned for more. But USAID is issuing progress reports, and here's some photos from recent progress reports showing the pile structure under construction, the airport runway behind it, and then the process of installing the heaters into the pile structure as I described. So in summary, Both these technologies, ISTD and IPTD, offer you a proven, highly effective way to treat SVOCs, including POPs, in terms of being able to meet both soil and air emissions standards. And the fact that we've met our goals on every project upon completion means that we can offer you a guarantee that we can meet the results that are required. Give us the information you have on the site. We'll design to those to that information, and then deliver what we've promised to do, and we do that repeatedly. This is a community-friendly process, safe and predictable. We have a lower carbon footprint than excavation, and many projects have been done adjacent to residential neighborhoods with no issues. So thank you very much for listening to the presentation. We're now ready to handle your questions, or to attempt to address your questions. So